I would like to talk with all of you about the new vibration shape toolkit. And so this is basically an extension that applies to both R-Flex and full flex bodies. So as you can see in the outline here, we're going to review the toolkit, talk a little bit about how things are working, what the theory is behind it, and then how this vibration shape is being calculated. Then we have a quick example to see what the steps are to use this toolkit, and then a summary slide. So here's some examples of this toolkit in use. So here we're looking at excavator mainframe. And so you can see, this is the RecurDyn simulation in the time domain, and then this is looking at the vibrational shape. And then similar thing here with this component, this torsion beam in operation, and then being able to look at vibrational shape of it. Next one here is this cross component here. And then its vibrational shape. And torsion, as we can see here. And then finally landing gear. So we're looking at the main outer strut, and then its vibrational modes. Okay. So that's what we want to do, is to be able to look at vibrational modes or shapes based upon simulation results in the time domain. So this can apply both to full flex and R-Flex bodies. And this is in the category of the post-analysis toolkits. And so this toolkit is using the node information from the target flexible body. And basically we'll see here the displacements are transformed using an FFT into the frequency domain. Then we can take that information and then actually be able to view it, as we see on these animations on the right. And basically with this kind of feedback, then the engineer can look at these results, and it helps guide decisions as far as how to address any kind of vibrational problems. So that's the purpose of this toolkit, is to provide that guidance. So how do we want to or how do we use this toolkit? So you want to pick a flexible body of interest, and that you want to be able to understand how it vibrates during operation. And this vibration that we can extract is really a function of the excitation forces. And so, one can select the area of interest. And then within that area of interest, there might be a region of maximum deflection or deformation. And that tends to be, related to the major cause of the vibration. And then using that, one can establish a vibration reduction plan, which could involve either, stiffening up the component at that location, or possibly adding some kind of constraint, and so forth. But the idea that you know what the vibration shape looks like, and therefore you can decide how to address it. So this vibrational shape toolkit, what kind of vibration shape is it really calculating? So we introduced this term called operating deflection shape, ODS. And it's a way to visualize the vibration of a flexible structure due to excitation forces. So under the loading that may occur during a RecurDyn simulation, different components are going to experience different types of vibration and noise that can travel through, the overall assembly. And so by taking displacement data of the flexible body, whether it's a full flex or R-flex, then we can do an FFT at the different nodes. And then actually the relative phase difference then is used to generate the particular vibration shape. So this ODS operating deflection shape is actually calculated without doing the more typical calculations of natural frequencies, mode shapes, damping ratios. It's not using that, it's using outputs from the time domain simulation. And you have the flexibility of defining any kind of a patch set, collection of nodes and elements that you want to have for your vibrational study. So, if here on the left, we see what's happening, throughout a simulation in RecurDyn with this toolkit, then we can identify the different vibrational shapes that are participating in the behavior of the overall system in the time domain. So then, how do we compare modal analysis with the vibration shape analysis? So in the case of the modal analysis, which can be done with the RFlexGen module, basically it looks at the mesh of the flexible body and the various inputs, and then it basically does an EnginSoft to come up with the natural frequencies and the mode shapes of that component. And so this calculation is done without looking at the excitations. The modal analysis outputs are basically telling us here's what is possible. Here are possible vibrational modes, and then the actual behavior of the structure, looking at the combination of excitation of the different modes and so forth, is going to be particular. But as far as the modal analysis, that information isn't considered. It's just saying here are the possible vibrational modes. In contrast, the vibration shape is calculated, from the work cycle of the machinery or the assembly in motion that's being studied. And so what this means is that if you have a vibrational mode and maybe there's no excitation for that mode, in the time, due to the time domain conditions of the simulation, then that mode, either may not appear, or that one can see, from the FFT results, what kind of magnitude it has, due to the excitation in the time domain. So let's see. So the point is that one can quickly assess, what vibrational conditions are occurring in one's particular product during the work cycle that's been defined. And then if one changes loading conditions and so forth in the time domain, then one will also see the response in the way that the vibration shapes are calculated, which will show the effects of changing loading conditions and maybe different input frequencies and so forth. So in comparing the operating deflection shape with the modal outputs, so this is kind of summarizing what we just talked about, but again, the ODS is looking at forced response results, and whereas the modal analysis is looking at just, vibrational characteristics of the structure itself and not looking at loading conditions. The ODS can be used for any structure or machine, regardless of what kind of resonance conditions may exist. And the modal analysis will show unique properties of that mechanical system itself. The vibrational shape with ODS can vary according to the load conditions, whereas the modal information is changing as a function of inputs as far as mass values, stiffness, damping ratios, or the change in boundary conditions. The ODS vibration shape can be obtained under various operating conditions that can be actually nonlinear. And you can also have time varying motions and so forth, and all of those conditions can be included. And the calculation, on the other hand, for the modal information is done, really looking at linear stationary type of motions being predicted. So let's look at the process for calculating the vibration shape. So we start out with a multi-body dynamics simulation with flexible bodies, which we call multi-flexible body dynamics, or MFBD. So some kind of an assembly of components, and some of those components may be rigid. The constraints between components may be rigid or flexible. But the studies that we do are going to involve the flexible bodies, and again, whether full flex or reduced flex bodies. And so then, we'll run the simulation. We'll have results in the time domain, as we see here, and those results will be expressed at each node in the flexible body. We'll take that displacement information, the FFT will be run on it automatically, and then we'll come up with, frequency, magnitude, and then the phase plot, for the various nodes in the system and the flexible body. And then that information will be averaged, and then it will go through this selection process, and then will be processed, with the sine waves. And then finally, that information will become then the various vibrational modes. So, as we saw before, for even a basic structure like this, flat plate, depending on the excitation, there can be various vibrational modes of interest that are related to the loading conditions. So here's an example. This is using the compliant clutch example. That's a tutorial, that's part of your regular RecurDyn installation. So if you go look at the tutorial section under the full flex, F-flex tutorials, this will be one of the examples that's just called compliant clutch or flexible clutch. So the steps here, the first step in general is to build your model. In this case, the model is available with the tutorial files. And then the next step is one wants to, carefully consider the simulation conditions, because this is where you set up, how many output frames or output steps with regards to the data at the nodes. So in this case, the simulation's running for 0.3 of a second, and then there's 1,500 output steps that are requested. And so that gives us a sampling rate of 5,000 hertz. So then you can run the simulation in RecurDyn, and then the simulation results will be produced. So that's all part of the first step. And we can see here the results in the time domain there in the lower right. And then next step is to go to the vibration shape toolkit. So again, this is post-processing menu is where it's found, and there's 2 icons. So first you go to that group, then you click the calculation icon, and then the dialog box that's shown will appear. And then you can pick the patch set that you want to work with. So in this model, there was just the one patch set, And so then that shows up. And then, you can, if you have multiple patch sets in your model, this add remove button here shown by the label 3 can be used, to remove patch sets from consideration, or if later on you want to add one back in, then you can use that button to edit which patch sets are going to be considered. And then you want to set the sampling frequency, and the dialog box will show you what the maximum sampling frequency is, which for this model is the 5,000 hertz. But you can sample at a lower rate if you would like, or you can go ahead and sample at the maximum frequency, but you select that here in step 5. And then step 6, you're going to show the what portion of the output time frame do you want to have considered. So if you happen to have a model that's settling out at the beginning of the simulation, you may want to start the starting time for considering the outputs for this vibrational study. You may want to have somewhat offset from the beginning of the simulation. And if you want to end it more quickly, then you can control that as well in step 6 here. And then step 7, you're going to define the directory file name that you're going to store these results in. And then once that's done, you can hit the calculation button and it will run the calculation for you. So then at this point, you're ready to look at some results. So the first step is to go to the animation icon here that was next to the calculation icon. And then it will, as before, show the different patch sets so you can pick which ones you're working with for the outputs. And then you can set up, the animation characteristics of, the, cycles, number of frames per cycle, basically. So in this case, 48 frames per cycle. And then the amplitude is just a scale factor. And, you'll want to adjust this to kind of get reasonable level of deflections. In this case, if it were me, I would probably make the amplitude factor a bit less, because I think these displacements are higher than I like to see them, but you can set that to whatever you would like to do. And then once you've done those steps, then you're able to, basically, bring up these plots, but then also be able to animate, show the animations at these different frequencies of the, computed vibration shape. So as before, the play button will display the animation, and then, you'll have feedback on the frequency of the animation, and you can kind of compare that to the, data here on the plots. So that's the steps there. And so you can, specify frequencies and then display the respective animations that go with that. So typically we're looking at the different peaks, as far as the magnitude off of the FFT analysis. And so, we're looking at the first, second, and third areas of peaks here. And so as we look at these outputs on these shapes, we can see that we're getting quite a bit of movement, really on both sides, the inner and the outer edges, but most especially on the outer edges. So then we can use that information to figure out how we want to improve, the vibrational behavior. So in this case, where we see all the issues at the outer edges, then what we show here is the introduction of bushings, at 4 locations on the outer edge. And actually, the effects of things like contact are not included here. directly. And in this case, we're kind of exciting the structure mostly in a two-dimensional sense, but we don't have a lot of constraints in and out of plane on this flexible body. So anyway, with the introduction of these 4 bushings, we can see that we go from the plot shown on the left to the plot shown on the right. And you can see the magnitude of the displacements, since we're looking at displacement outputs, the magnitude of the displacements has decreased a lot. And that's why we get this relatively flat curve on the right-hand plot. So that's the point of this toolkit. Understand things, understand vibrations as expressed in the time domain. One of the things this avoids is that if you have different mode shapes, different modal frequencies, from a modal analysis, it's maybe hard to focus on which mode shapes are, need to be dealt with. And with this method, you can look at the mode shapes that have the high magnitudes and then address those modes, as compared to trying to address all the different vibrational modes, and maybe some of them are not being excited anyway. So this helps you see what's, that fact. So in summary, as we've seen, this toolkit is, part of the post-analysis toolkits, and it's really for analyzing and understanding vibrations. And it's using this operating deflection shape, which is including all the conditions occurring during the duty cycle, in the time domain. And so, we can visualize vibrational shapes, and we don't need to separately calculate natural frequencies and mode shapes. So if they're not known, that's okay. We can directly move to the vibrations due to the operating conditions. And, with this capability, we can get vibrational shapes that might be changing a bit due to loading conditions. And we'll be able to see those effects, which we can't see with the modal approach. And then looking at the results, we can then establish a vibration reduction plan, to figure out, what kind of structural changes to make or what kind of constraints to add to the system. And so then, by doing that, we can reduce vibrations in the machinery. And, we do that by looking at the locations with the maximum deflections. And we can do that, get a feel for that visually. We can also get a feel for that by looking at the plot, of the magnitude coming from the FFT. And then as far as future activities, with this release in V9R5, we can work with a particular patch set, but in the development plans are to add capabilities to actually look at the vibrational shape, for the entire multi-body system. And, in years past, people have done this sort of thing in a linear sense, looking at modal representations of the flex bodies, and then trying to combine that together. So that's a linear approach, but with what we're going to have with this enhanced version, it's really a way to look at vibrational shapes really for a nonlinear system, that includes all the operating conditions and loads.